So basically, that in a very PV,
Hello,
you can do either
is the audio working?
if you
Okay.
maintain equity all the way.
Joined who? वेट सो अभी रैपिंग अप वगैरह वगैरह दिख रहा है मुझे, ठीक है, और कुछ सुनाई नहीं दे रहा है।
हेलो, सुनाई दिया?
ठीक है, अब मैंने माइक ऑन किया, मेरा आवाज आ रहा है, मेरा आवाज आ रहा है। हेलो हेलो 1 2 3 चेकिंग चेकिंग 1 2 3 माइक चेक 1 2 3 माइक चेक।
Hello, we can hear you.
Yes, thanks।
Testing, testing. 1, 2, 1, 2. Ah, now we have a true full name. Say again? It is on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, no, you shouldn't push it longer. I'm running out of numbers.
Start the next session, and we start again with Jakob, and this is about end-to-end verification for subgraph solving.
Thank you. So happy to be back again and talk a little bit about proof logging, certifying solvers. This is joint work with Stefan Goch, Kieran McCreish, Magnus Merén, and the Ertel and Yonkiam Tam. And so we already had a full session for those of you who are here on proof logging, but I wanted to take a step back and just say, talk a few more slides about proof logging in generality. Why do we do this? Well, we do it because for satisfiability, but also we want to do it for constrained programming, for mixed integer programming, SMT solving, because all of these solvers are amazingly fast. Since the turn of the millennium, they have really revolutionized how combinatorial optimization works, but they're sometimes wrong. And when you run these solvers, there's no way of knowing when they claim that an instance is infeasible or they claim to have found an optimal solution or a lower bound. How do we know that it's even true? And in fact, we know the opposite. There's ample evidence in the literature that solvers, even the most mature solvers in academia and in industry, can get it badly wrong. And what could we do with this? Well, we can do testing, but the point is testing can inherently never prove the absence of bugs. It can only detect their presence. So software testing is not going to solve this problem for you for a very, very fundamental reason. Also, we can't use formal methods to build formally verified solvers because modern solvers are far, far, far too complex. This is not me telling you this. This is the formal verification people saying they fail to even build good SAT solvers. And we're not even talking about constraint programming and mixed integer linear programming. So the only game in town that we have, the only realistic approach we have is proof logging. To make solvers certifying so that they don't only give you an output, but a proof this out. So just to make sure we're all absolutely on the same page, what do we mean? Well, we run the solver on an input and get an answer as before, but we also get some kind of proof file. We can then take the input, the answer, and the proof file and feed to a standalone proof checker. And then we look at the verdict of the proof checker, and it will tell us whether the proof establishes that the answer is correct for this. Now, in order for this to work, on the one hand, we want to run a certifying solver, a solver with proof logging without slowdown. So it has to be very easy to write the proofs. But the solver is doing tons of complicated reasoning. So that means that the proof system has to be very, very powerful so that you can write your proofs in a concise manner. On the other hand, the whole point is that we don't trust the solver precisely because it's doing so much complicated things. We want the proof checker to be a very, very simple piece of code that only checks completely trivial derivation steps. That's how we're going to trust the proof. That's how we're going to trust the verdict. Now it's very clear that, you know, we're asking for two pretty opposite things. We want an extremely powerful expressive proof system that is also dead simple. The question is, can we have it both ways? Maybe this is a little bit too good to be true. And in fact, I would argue that it has, what we've seen so far is that it is, in fact, if you go back just 5 years in time, 3, 4, 5 years in time, it was too good to be true. We're talking about that proof logging for SAT has been a major success story. That is true, but it's also equally true that unfortunately, that up until just a couple of years ago, if you wanted to run in the SAT competition, you had to switch off things like Gaussian elimination, things like symmetry breaking, because there was no efficient proof logging support for it. So SAT proof logging had simplicity, but not sufficient expressivity. Constraint programming, you had the same type of problems, and also MaxSat, that you cannot get a simple enough proof system that is expressive enough to proof log the actual advanced solving techniques that you want to provide certification for in a state-of-the-art solver. And I also want to remind you that it's very important in this context when you're working on combinatorial solving to eat small enough. So thank you for that. So my main message, and the message of the whole previous session is arguably, I think that we don't have to give up. I mean, this trade-off between expressivity and simplicity, you can find a sweet spot. In fact, you can find, miraculously, there's a single unified method of proof logging that seems to be able to take care of pretty much anything we've thrown at it so far. Of course, SAT proof logging is amazing. We should not throw it away. We should use it, but we should lift all of the nifty SAT proof logging techniques from clausal constraints to 0-1 integer linear inequality. This has been implemented in VeryPB. It totally works. As we've seen, there's room for software engineering improvements, but VeryPB has really taken proof logging and brought it from a large portion of SAT solving, but not everything, to all of SAT solving and MaxSat solving and constraint programming and beyond. Even to problems that are not representable as 0-1 integer linear inequality, which raises the question, like, what do you mean? If my problem is not of 0-1 integer linear inequalities, then how can I use 0-1 integer linear inequalities to do my proof logging? So what I want to do in this talk is to explain how do we do proof logging beyond SAT and even beyond 0-1 integer inequalities using this simple formalism. And I'll try to do so by giving you an example of what I think is a highly non-trivial application. I'll show you how to do subgraph solving, to do proofs for subgraph solving in a proof format that doesn't have any idea what a graph is. Okay? We're going to prove things, highly non-trivial things about vertices and edges and how they're connected without even knowing what vertices and edges are in the proof format. A priori, this just doesn't make sense. Okay, so at the end of this presentation, my goal is that it should make sense. And not only that, not only will I tell you how to do proof logging for subgraph solving, I'll tell you how to get this in a fully formally verified setting, so that, you know, supported by the gold standard of formal method experts provide, like the highest form of formal verification. So this is the purpose of this talk. Okay, but for a few more minutes, I'll try to be general. This sort of came up in the first session a little bit, but I want to make it explicit that our goal is not to throw away all existing solvers and build new solvers from scratch that somehow have to work within this new formalism. This is very, very important. Okay, our goal is to take existing solvers that are highly optimized. People spend years working on them. And basically, we just want to insert well-chosen print statements so that these print statements somehow magically provide a fully correct formal proof with 0-1 integer linear inequality. What we're shooting for, we also want this proof logging to be very efficient. For proof generation, a small constant fraction overhead in running time, maybe 10%, something like this. Because we want so small proof logging overhead, and because the proof system is so simple, we're willing to pay a little bit more for actually checking the proof. The SAT competition has something like a factor 10. So if I solve the instance in 1 hour, then worst case checking the proof might take 10 hours. Okay, of course, it would be great to bring this down, but this is sort of what we're shooting for right now.
So Amazon wants smaller than one, so one order.
Yes, I agree that would be great, and I think it might be achievable, but we're not going to talk about it in this presentation. But it's gonna, I think, any proof logging is going to scale linearly, at least with the solving time. So if you're a theoretician, then you're used to maybe like running, being able to check the proofs even in logarithmic time or something. That's just not going to happen because we're building the proof in an online setting. We don't even know what proof we're building up until the very last millisecond where it's like, oops, this was what I was proving all along. So you're going to probably have linear scaling, at least. Okay, maybe if you want to post-process the proof and save it for auditing reasons, then maybe you could do some post-processing to get the verification down even further. But like the first verification, I think it's going to scale linearly. Getting below a factor 1 would be great. But even 10, as you saw in the first session, we're sometimes looking at 100 today. So let's take one order of magnitude at a time. And then a design choice that we have made, and you don't have to make this design choice, but we want the proof language to be dead simple. So we want a proof format that can talk about Gaussian elimination, XOR constraints. It should talk about constraint programming propagators like all different and Hamiltonian circuits and everything. It should talk about symmetry breaking, but it shouldn't know about all different. It shouldn't know about groups and permutations. It shouldn't know what Gaussian elimination is. We just want a very, very simple proof format. But somehow the underlying proof system should allow us to reason about XOR constraints and symmetries inside the proof. Okay. And because the proof system is so simple, so that if we want to talk about the problem with XOR constraints or with CP propagators, then obviously, there's going to be a translation from these concepts down to our very simple proof format. And therefore, we want to combine proof logging with a formally verified proof checker that, among other things, will check that our translations make sense. Okay. So our language, as you've seen a number of times now, our proofs are going to operate with 0-1 integer linear inequalities. So basically, just without loss of generality, positive linear combinations of literals greater or equal than some integer, and the coefficients are also integers. Okay. And just to make sure we're all on the same page, note that CNF is a special case of this. A clause is just summing up the literals and saying that at least one of them is true. But you have more expressive constraints like cardinality constraints or completely general pseudo-Boolean constraints. And what is a priori not at all obvious, but which turns out to be true, is that this simple formalism, together with fairly simple ways of manipulating these 0-1 integer linear inequalities, allows you to do efficient proof logging for even the most advanced techniques in Boolean satisfiability solving. We saw in the first session, it allows you to do proof logging for SAT-based optimization. You can do it for pseudo-Boolean solving. I'll tell you about subgraph solving in this talk. You can do it for dynamic programming, decision diagrams, 0-1 integer linear programming, constraint programming, and the list is growing as we speak. It's not at all obvious why 0-1 integer linear inequalities should buy you all of this. It's not something that I would have told you like 2 or 3 years ago. It just seems to be like a freak accident, or we're freakishly lucky that this just works. And it somehow says something interesting also, that all of these very, very different algorithms, it seems that under the hood, all of these smart things that these people came up with in these different combinatorial optimization paradigms somehow weren't that much smarter than the cutting planes proof system in proof complexity together with suitable strengthening rules. So there's some kind of unified underlying theme, which I think is scientifically also very interesting. Like under the hood, are all of these different algorithms actually doing the same thing? Because if they aren't, then why can we use a single proof system to provide proof logging for all of them? Okay. So how do we do this type of pseudo-Boolean proof logging with 0-1 interlinear programs? Well, if your problem is already a 0-1 ILP or a CNF formula, which is a special case, you're in luck. You just add print statements to your code and you're done. Can't be that hard, right, Dieter? So it's a done deal. Otherwise, what you'll have to do is you'll somehow have to translate your problem to a 0-1 interlinear program. And then you'll do your proof logging for that 0-1 ILP representation. But it's very important, addressing a confusion that arises when you submit papers and reviewers look at them. Your solver is not going to be a pseudo-Boolean solver or a 0-1 interlinear programming solver. If we're doing a graph problem, the solver is going to work on the vertices and edges, but the print statements are going to somehow convert these reasoning steps to 0-1 interlinear inequalities. Again, it's very important to understand we don't change the solver. The solver is going to do its reasoning. We just need to represent it in this other formulas. Okay? And as I've told you maybe like 10 times so far in this presentation, maybe I'm losing count. Why are we doing 0-1 interlinear inequalities? Well, it just seems to be, it's a simple formalism. It's close to clauses, but it's much more expressive. And as an example, like take your favorite NP-complete problem and think about the reduction to 0-1 interlinear programs. Chances are you can think of a very natural and clean one. So it's like it's a nice formalism. It captures lots of problems. And at the same time, going from clauses to 0-1 interlinear inequalities buys you a lot in terms of reasoning power. In fact, we understand in theory that you can get an exponential increase in reasoning power by going from resolution, which is the proof system underlying SAT, to the cutting planes proof system, which is what we are using. Yeah. But note now that the framework that I told you about before changes. For instance, in a graph solver, you're not going to feed the input to the checker. The solver is like going to read the graph, and then it somehow decides, oh, I have this re-encoded 0-1 ILP in mind, and the proof is going to be in terms of this encoded input. And this now raises the question, well, how do we know that the actual input and the re-encoding that they actually sync up? Okay. And in the first step, what we've done so far, you can say, well, this is not what we're worried about. We're not worried about, like, you know, representing matched cliques, say, as a 0-1 ILP, because that's trivial. We're worried about what's happening inside here. But of course, if you want fully formally verified results, then you shouldn't be happy with this. And indeed, what I'll tell you about this, you will have a slightly more complicated or advanced setting where there will be a formally verified checker that takes the actual input and that will sort of check that the input and the re-encoding that they do sync up. And then it will read the proof, or actually it will read a slightly simplified proof that the checker provides and check that the elaborated proof, so-called elaborated proof, establishes that this is the correct answer for the original problem. So this is like the full workflow, intended workflow on formally verified checking. Okay. And now I want to tell you about how do we do this for subgraph problems. What are they? Like, for instance, finding the maximum clique in a graph, finding isomorphic embeddings of a smaller graph into a larger graph, or you're given two graphs and you want to find the largest common connected subgraph of them. The best solver on the market today for these problems is the Glasgow subgraph solver. There are also other solvers, but I think usually the Glasgow subgraph solver is best. Sometimes it's the only solver that will in fact return a solution. And the question is now, how do we know that this solution is optimal? Or it will tell you that there is no subgraph isomorphism. Like, can we trust that this is correct? And of course, we know how seriously the people in Glasgow take their software engineering. They've tested it thoroughly, but still. And we want to add proof. So the way to make these results really trustworthy is that we want to add proof logging. And a couple of years back, we showed that if you take what the Glasgow subgraph solver does, you can formalize it as reasoning with 0-1 interlinear inequalities. So that what the solver does, these print statements, whenever it applies a reasoning step, it does some local print steps. And these local printouts somehow compose into a global correctness proof that can then be checked by this verifier for pseudo-Boolean proofs. And note that the slightly weird thing is you're just going to have the proof is going to be a sequence of 0-1 interlinear inequalities. There are going to be no graphs inside. Okay. So let me try to very, very quickly sort of give a little bit of a flavor, like how would this work for subgraph isomorphism, to take a concrete example. So what is subgraph isomorphism? We have a small pattern graph P. We have a larger target graph T. And we're interested in finding all subgraph isomorphisms, or just think of one really for now. So what's a subgraph isomorphism? It's a mapping of the pattern vertices to the target vertices, which is 1-to-1. And is such that if pattern vertices A and B map to target vertices U and V, and AB is an edge in the pattern graph, then UV should be an edge in the target graph. This is sort of, I mean, it should be an isomorphic embedding. Okay? This is the problem. So now we need to somehow write this down as a 0-1 ILP. And how we'll do this, and where I'll, for simplicity, let's assume that the graph doesn't have the graphs don't have any loops. This is not material, it's just, you know, to keep the presentation clean. So here is a 0-1 ILP, which I claim is subgraph isomorphism. So there are variables XAV, which are indexing over pattern vertices and target vertices. So ABC are the pattern vertices, UVW are the target vertices. Every pattern vertex A has to map somewhere. This is what this constraint says. Like for every pattern vertex, sum over all the target vertices, and you have to get a sum exactly 1. Okay. Also, the mapping is 1-to-1. So this second constraint says that, well, a single target vertex U can only accept one pattern vertex. Okay. And then this third constraint says that edges are preserved. What I'm saying is that if you can read this as an implication, if A, pattern vertex A, maps to target vertex U, and if B is a neighbor of A, then B has to map to one of the neighbors of U, because otherwise I'm not preserving the edge. Okay, does this make sense? So then our first leap of faith is to say, well, this is subgraph isomorphism. Is there a question on this?
Are you assuming a complete graph? Because you would also want to map non-edges to non-edges.
No, I don't care about this. Is a subgraph isomorphism. This is not graph isomorphism. It's I'm embedding the smaller graph into the larger graph. I don't care about non-edges. It's not an induced embedding.
Sure. Great.
Make sense?
Right.
Okay. Okay. Then what the Glasgow subgraph solver will do, it will apply a massive amount of reasoning, in particular, a massive amount of pre-processing. You can immediately see, for instance, and look at A, it has 3 neighbors, B, C, D. There's no way we can map it to U in this target graph because U just has too few neighbors. Okay, so this is like the simplest form of pre-processing. There will be much more advanced cases, but this is, I'll barely make this fit on a slide, so that's why I chose it. So how would we, so basically the solver will count neighbors and it will figure out that without loss of generality, X and U is false. This is what we'd like to derive. How do we derive this? Well, we say if A maps to U, then B has to map to one of the neighbors. And we say the same for C and we say the same for D. These are these constraints. And then we say, well, V and W, they're only willing to accept one vertex. These are these constraints. And then we just add some non-negativity constraints that variables are non-negative. And then we sum everything up. And then we get that 3 times negated XAU greater or equal 1, which you realize means that this is just saying that actually XAU has to be false. And what is not at all obvious and what I don't have time really to tell you about in detail is that for this kind of techniques and much more advanced techniques, it turns out that the solver reasoning maps extremely nicely into cutting planes proofs. You don't even need this. If you were confused about the redundant space strengthening and all this stuff, we don't even use that. We just use clean implicational cutting planes proofs. Okay, so problem solved then, right? I mean, we said that solvers are complex, we cannot trust them, but we have pseudo-Boolean proof logging, right? But two problems. How do we know that the very PB proof checker is correct? I mean, spoiler alert, it also contains bugs, sadly. No, it's of course, that's what happens when you outsource the coding work to PhD students. But also, actually, how many of you would bet, like, are you willing to bet $1,000 that the encoding I had on 2 slides back, was it correct for subgraph isomorphism? You were nodding before, right? $100 at least, or $10? So you see, the question is, can we really trust, the proof checker? Can we trust the encoding? And we're not willing to do that. So what we will do is first, we'll make a verified encoder with formal methods that actually establishes that solutions to the original problem and the 0-1 ILP isn't like a one-to-one correspondence. Okay. And then we'll take this so-called augmented proof, I'll talk about it in a minute, that the graph solver was spitting out. And it's a little bit too complicated for formal verification because it requires proof verification, proof checking, and requires search. And that's heavy to formalize. So what we'll do is we'll instead define like a subset of very PB proofs. So the augmented proofs is what the solvers write. It contains a lot of powerful proof rules that are nice to give efficient proof logging. But then there's a kernel proof format that removes things like, for instance, reverse unit propagation. Okay, so only explicit, any rule you want to use, you have to tell explicitly what the rule is. And what very PB can do, it can take an augmented proof and simplify it to a kernel proof. And now when all search is gone, all unit propagation is gone, now you can build a very efficient, formally verified proof checker. So back to our plan. So once you have this augmented proof, you run it through an elaborator that gives you a kernel proof, which you can run to feed to the verified checker together with this verified encoding, which is guaranteed to sync up with the original graph problem. And then the verified checker tells you that you can trust the code. Okay. So now, what does it mean then? Now it's fully formally verified. So what does that mean? Well, that means that what you have to trust is the math definitions of the problem. We still have to define for the graphs what subgraph isomorphism is, right? We have to define what a clique is. But it's hard to get around that. Like, how do I know that I'm solving clique if I'm unable to give a mathematical definition of clique, right? So somewhere you have to trust that I know what I'm talking about. So this you have to trust. That you have to trust something, and this is the bare minimum trust required in formal. Like, this is the gold standard. It doesn't get better than this. This is what it means. Verified checker for. And that is checking. But that doesn't need to change. You always have. Front ends, but they are fairly easy to build by the same methods that in the first session that we front end from. Front ends that sort of different types of problems. That's it. So able to compose proof, extend this automated planning is something case complete mixed integer. The SMT community takes proof very, very soon. But even there are some theories with like bit vector reasoning. Seems solving and proof helpful here. And then proof logging opens up a whole analysis. Lots and lots of programs. And hiring, so talk to me if don't talk to the I don't talk to Bart, I mean. Tutorial solving is but correctness is the way testing doesn't solve this problem, formal verification doesn't solve this. Logging with is the best. When you're picking your is and if you're worried about the simplicity, as I showed you, you can combine. Now you should go home and check how you should use.
Time for
Practical question. So for the proofs you're getting for these graph problems, how large do they get? Is proof size already a problem, or is it?
Proof size is the problem. Verification time is a problem. For the main problem algorithms, there will be a lot of bit parallel reasoning, hundreds of bits parallel with lots. When you're checking the proof, you have to work on like your individual. So you're actually looking right there.
And in
so case for proof, nowhere close to being able to run it like in condition settings, say, but you can still, what you can do is we can totally run it for problems where the Glasgow subgraph solver that gives an answer. Generate proofs, such instance. So it's sort of a way of natural NLP have a non-edge and both vertices. Suppose course graph. Graph will be the 0 NLP and this is a so but then you can think about, okay, do I really need the representation, or should they have edge axioms for this list of, I mean, you axioms.
Yeah, want to find out, and then you actually mentioned it under here that bit vectors are, of course, exponentially more succinct than time complete, MP complete, and this solver is using bit vectors. Wouldn't it be better to have, so I'm proposing AP. Of course, it will be very difficult in future talks
we don't have anything published and there's tons of work, but it seems like 0-1 interlinear programming is sufficient to do everything that state-of-the-art automated planning solvers do. And this is already p-space hard. The point is somehow that is not XC class have yes verifying arithmetic paper. It and algebra. That's I mean, there is a like strong aesthetic of seem to be getting away with it. Or ever have covered all of at this point.
So it looks like you can verify solutions to both decision problems and computation problems. Verify for bit vector solving and computation. So my question is whether you see a gap in performance when you try like this optimization problems. In SAT and MAXAT, for example.
For some MAXAT factor 100.
There might be a gap.
But we're working. I guess optimism.
Okay, so the next talk is hello everyone.
And first of all, I'll explain a bit what the Young-Baxter equation is. And it's an mechanics. However, it also has many more known applications. That means that a lot of people find out more. However, integrating all solutions is still an open problem. And it is quite a hard one at that. Without any additional assumptions, highly uncertain. So we focus on enumeration that is of and ring So that is why we are focusing finite set theoretic solution to be very highly specific. And the nice thing about these solutions is that we can study them in equivalent mathematical squares. And those are the non-degenerate cycle sets. So what is a cycle set? Well, it is a tuple that consists of a x and a binary operation, which I'll denote. And we want this binary operation to still sum. And first of all, we want this map phi x to be bijective for all x's. And then second of all, we want this equation to. And this is a very important equation. It's a cycloid equation, and it actually gives us a. And then we are focusing on degenerate cycle sets, so we also want x to x dot x to be. And that means that our cycle set is non. And why are these cycle sets so interesting? Well, cycle set, as long as this set x is finite, can be represented by a square matrix. And in this square matrix, we are going to take a y, and we are going to value of x dot y in it. And that allows us to represent all of these cycle set definition in terms of our square matrix. So we can actually quite easily express this problem in terms of a common. And that allows us to actually enumerate these solutions. However, in practice, mathematicians are not interested in enumerating all possibilities. They are often only interested in enumerating non-isomorphic. So when our two cycle sets are isomorphic, they are isomorphic by a bijection such that the following. And this is the definition. So that means that we can now find out when cycle sets are isomorphic, and we can also use isomorph to determine the image of a cycle set under this given. And we are given a cycle set and its associated matrix here in the matrix, and we are given an isomorphism. So how can we now determine the image of C? First of all, we are going to apply the permutation phi to the rows and the columns of our matrix, and then we are going to apply to all of the entries matrix that. And that gives us the I. And now if we want to enumerate only non-isomorphic, then add symmetry constraints and only enumerate lexicograph. And we can do that by just comparing the values in order and different. So see color. And if the same thing holds all of the isomorphisms. And this is a technique that was already done. So my co-author, Leandro Vendramin, and he have already tried to enumerate all finite cycle sets of certain sizes. And they did this up to size 10. So they modeled the cycle set constraints as a common problem. And then they partitioned the problem by fixing diagonals. And that is a technique that is based on a proposition that tells us that diagonals that are conjugates in a symmetric group actually define isomorphic. So that allows us to choose representatives, conjugacy classes, and to fix them on the diagonal. And that allows us to do things. First of all, it decreases search space, and second of all, it allows us to parallelize them. And then for each instance, we can add static symmetry breaking constraints, and then we can enumerate all these solutions. However, we know that complete symmetry breaking, forming complete breaking using breaking constraints is infinite. So that means that if we want to only enumerate isomorphic solutions, isomorphism check at the end. So that is what we want to get rid of. We want to get rid of final expensive isomorphism. And we are going to do this by using a different technique, a framework that we recently, and we are going to use SAT modulo. And the main goal of this is satisfying non-isomorphism. And it was actually introduced cases in mathematics in mind, and it will create graphs with properties. What is the core idea of this framework? Well, we are going to include mathematical as a property, and then we are going to generate only, and we are doing this during the. And how can we do this? Well, first of all, we are going to work together with our subsolver. And we are going to ask it for partial interpretation that it is working, partial assignment. And then we are going to check that assignment and verify whether it can still become lexical. And if we are sure that that is not the case, we are going to force the current branch of the. We are going to do this by learning. So that modulo symmetries already exist. All the minimality check that checks whether we can still become lexicographically minimal already exists for several mathematical structures. So why are we presenting this here? Well, minimality check needs to take certain things into it. First of all, it needs to take into account the encoding of the mathematical problem, and it needs to take into account the structure of our isomorphism. So that means that we out the cycle set. So what do we have? Well, we have a property of variables, and if we find an assignment, that means that we have found a cycle set. Now, what we want to do is breaking constraints during the solve. But during this solve phase, we might not know cycle set. We might know that some values are already decided. We might know that some values are impossible. So we need to reason about something. We are going to reason partial cycle. And what is a partial cycle set? Well, it is a matrix again, a square matrix, but instead of values, contains. And these are the values that are still false. So if we are given a partial assignment that we obtain from our subsolver during the search, we can associate it with a partial cycle set, and this partial cycle set is going to represent exactly those values will be true. So I have made a little example. We have the partial cycle set. And we can see that the first row is already fully consistent. And then on the second row, we can see that not all values are defined yet. The first cell can either become 1 or 2. So that means that P can still be extended to one of several fully defined cycle sets. And we are going to collect all of those fully defined cycle sets in the set X of. And what we actually want to find out is, can P still be extended to a lexicographically? So we are going to say that the partial cycle set is graphically minimal if this is. And when is this not the case? Well, it's not the case if for extensions find a breaking symmetry. And we know that P cannot be minimal. But it's very hard to decide this because then we need to find all of those extensions and we need to find breaking permutations of all of those extensions. So that is a lot of work and it would take a very long time. So we want to do some, and based on the original modulo paper, are going to do something. Because if we can find one symmetry phi, such that the image of the extensions under phi is strictly self, a breaking permutation that breaks all of the extensions, we also know that P cannot. And we are going to be looking at those permutations, such a permutation. So how can we find the witnesses without enumerating all of the extensions? Because then we would end up in the same problem. So we need two things. First of all, we would like an order over partial cycle sets, and this order needs to be a very specific characteristic. What we want is that if we find out that a partial cycle set P is strictly smaller than P prime, like the same thing to all of the extensions. And then second of all, we would like a way to apply permutations to. And if we have both of those things, that means that if we can find a permutation pi, such that the image of P under pi is strictly smaller than P, And we know that the same thing holds for all of the extensions. We have found ourselves without enumerating all of the extensions. So that is good news. So first of all, how do we apply a permutation to a partial cycle set? Well, it is very similar to applying a permutation to a fully defined cycle. First of all, we apply the permutation phi to the columns of our partial cycle set. But then there is a small issue because we want to apply the inverse permutation to the entries of our cycle set, and now we have sets in entries set of values. So we need to apply the inverse permutation to all of the entries. And that gives us the image under pi. And now we want to find out whether the image of p under pi is strictly smaller than p itself. And if the values are already defined, it is fairly simple. We can just use lexicograph. We compare all the cells, and whenever they become different, that value to find the strictly smaller than 4. But things become slightly harder if we need about cells that are not fully defined yet. And in case we can see that our image has the value 2 itself, and the whole cycle set could either become 3. But the good news is that 2 is smaller than both 3 and 4. So as long as that is the case, we know that this is smaller than all of the extensions. We are going to use that kind of reasoning to find our. So when is p strictly smaller than p prime? Well, if we can find the cell C such that the maximum value of C is smaller than the all the cells that come before that cell want their maximum values to be strictly smaller than values in. And similarly, we could define what it means smaller than or equal. And that is the case logically when either p smaller than p prime, or when for all cells C their maximum values in smaller than or equal to values, the minimum values in prime. So now we have an order and we have a way to apply permutations to cycle sets. So we can start looking at because we have exactly what we need. Smaller than p prime, or if the image of pi is strictly smaller than p, we have found ourselves with finality because we know that the same thing holds all of the extensions. And we have a nice side effect as well. If we find out that the image of p under pi is smaller than or equal to, and p is not fully defined yet, that means that we can propagate information through us because there are values that we can get rid of in the that are not full. So that is good news. So what is the goal of our minimality check now? Well, we want to decide whether there exists a permutation that is an isomorphism of a problem such that can either get rid of p, if witness of non-minimality, we can safely get rid of p, or such that we can propagate information. And could either consider all of the possible isomorphisms of our problem one by one, all of these permutations, but once again, that would take us a very long time, so we're not going to do that. But inspired by the original paper, we are taking a different, and we are going to perform backtracking over the space of all permutations. So first of all, we would like to represent possible permutations using not just a single list, but using nicer data structure. And we are using the, and we can see that this is a part that we are dealing with, and we map in the. So this order partition represents possible permutations, 3 map 1 and 1. So start with an ordered partition that represents our possible isomorphism problem, and then we are going to make a decision. We are going to split a partition and then the rest, and then we are going to propagate it because we want to first of all ensure that our permutation can still be extended to an isomorphism problem, and second of all, we want to ensure that the image of p under pi is smaller than or equal to, because making p larger, making the image of pi larger will not be fair. And then we are going to repeat steps until either we have found a useful permutation or until we are sure that there is no permutation. And I'm going to walk you through a little example to make things. So I have quite a large partial cycle set here, and I've marked the diagonal in because it is fixed and it needs to remain fixed. So that also means that our symmetries that we can take into account, the symmetry problem that we can take into account, also need diagonal invariance. So that means that we can use this to create an initial permutation pi, which is down here, in order to ensure that this is the case. And then now we want to find out whether there exists an extension of this permutation that we can extend in order to use fine or partial. And start off with our partition, with our permutation. And first of all, we could decide that the permutation of 1 is 1. And then we propagate in order to ensure that our diagonal remains fixed. Permutation of 2 is 2. But we don't have enough information yet to decide whether I is larger than or. So we make an extra decision and we decide, for example, that the permutation of 3 is 4. And then we propagate again in order to our diagonal remain fixed. And we find out that our image is larger cycle set. So we need, and we make another decision and we propagate and we find out that none of it works, so we backtrack even. And we might decide that instead the permutation of 1 equals propagate in order to a decision, permutation of 3 propagate, diagonal remains fixed, and we have found a witness on minimality because our image is smaller than the cycle set. So good news, we can get rid of P. So how do we get rid of P? Well, we are going to add a class to ensure that the solver backtracks. And what is a class that we are adding? Well, you know what it means for this permutation pi to be a witness of non-minimality, because it's a very nice definition telling us what it means to minimality. So we are just adding a class that tells us, well, one of these conditions change, and if that is not the case, and for propagation, things are very similar, because if there is a class, if there is a value that we can get rid of, that means that that value would make our partial cycle set not lexicographic. So very similar. And we implemented all of this using Radical together with the EPUB interface. And this interface allows us to keep track of the current assignment, to add clauses while during the phase without having to restart, and to choose variables to decide on. And both the implementation and the database that we have constructed are available. And we did some experiments. And first of all, we wanted to find out which was a good configuration to integrate solution. And the first thing we tried was, is it worth partitioning against these diagonals? Is it worth fixing these diagonals? And we can see that indeed, fixing the diagonals makes our search space quite a bit smaller. Our number of conflicts goes down quite heavily. And we can see that it also has a huge impact on the time use. Second of all, we also used some different codings for fixing diagonal. We could add unit classes to fix the diagonal and trust our SAT solver to propagate whatever it needs to propagate. Or we could do that ourselves already, just get rid of everything we don't need anymore. And we can see that indeed it is a small but positive impact to already do propagations ourselves. Then we could also verify whether it's actually useful to check partially defined cycle sets and to already get rid of them. And we could check all of the partially defined cycle sets, or we could only check a few of them. We could check 1 in 5 partially defined cycle sets, check 1 in 25,000 partially defined cycle sets. And we can see that here, we need to find a balance between checking enough cycle sets that the conflicts go down, but not too much, because doing this check, of course, incurs an overhead. It takes time to perform this minimality check. However, in order to limit this time usage, so decide that if we start checking a partial cycle set, I decide to abort the minimality check if it starts taking too long. Because we only need to guarantee that completely defined cycle sets are checked at minimality. So we can decide to, for example, abort the check of a partial cycle set after 200 iterations in the backtracking situation. And we can see that this has a very positive impact. So we are doing this. And then last of all, we can also verify whether it is useful to propagate information instead of only excluding cycle sets, also excluding values in. And this has a small but positive. So we ended up using this fast configuration in order to integrate as many solutions as we can. And we can see that indeed we were able to enumerate all solutions, cycle sets of size 10, and we compared our timings against the timings from paper by Rami and his co. And here I have a nice column with speedups, and we can see that the speedups are quite nice. I'm happy to report that we have speedups, but the bad news is that instead of a very extensive isomorphism check, we now have a very extensive linearity check. So we started wondering, why is this the case? And this is where the bad news goes. So very nice graph, and I think that everybody can see where the bad news happens. There is one thing that takes quite a lot of time. It's this purple here. And it takes a lot of time to verify whether minimal cycle sets or completely defined cycle sets that are minimal are indeed minimal. And we were wondering why this is the case. Why is there this huge purple graph? And then we wondered, is this problem as problematic for all diagonals or some diagonals? And we can see that for the diagonal that has the identity on the diagonal, so just etc., it is a lot more problematic than for all the other diagonals counted together. So why is this the case? Well, if we are dealing with the identity diagonal, we need all of the n faculty. So that means that we have literally no information to propagate during our search for useful witnesses. So that is a lot of work. There's a lot to consider there. And that also means that we were not able to expand on the original paper because we need on this diagonal case, identity diagonal case. And there are a few solutions that we have identified. First of all, we could try to get rid of this need on this final check if we can guarantee that it's complete. Or we could try to identify other propagation to propagate, and we could try to integrate other graph canonization algorithms in order. Then second of all, for future work, we could also look towards certifying the results, because we have obtained the exact same number of solutions as in the original paper, but that only means that we are either both wrong or so that has not really any value. However, we have looked into verifying this and verifying whether we have enumerated exactly one solution per isomorphism task turned out to be quite a hard problem. So it is still an open problem. And then last of all, the tool that we have made here, it can also be used to create related structures. So it could be used, for example, to enumerate biquadrals with very limited adaptation, and these have applications in non. So that is what we have done. We have reproduced results from the original paper, but with a significant step, and we are very close to creating also these results for size 11, except for this density diagonal. And we did it by extending the submodulus framework in order to out these partially constructed cycle sets. And this current technique can also be adapted minimal adaptations in order to renew. Thank you for the.
Thank you. So my question is, have you also modified the decision heuristic of the solver of Cadical?
I tried a few things out, and I ended up using the first value that was not sort of. I'll just go back to cycle set. So I went with the first pair that had still an undecided value, and I picked the smallest value in that set. And I tried some other things as well, but this ended up being the quickest. But I know that there is still so many options there to try out. So if I find something better, I'll let you know. Or if you have any ideas, please let me know.
Not yet, at least.
I think like you have the option to, whenever it does, yeah, whenever it does not propagate, I
maybe a small remark is that even if you would have the perfect decision heuristics, that always gives us immediately all solutions and then some magic box that tells us, no, there are no further solutions. So the perfect solver is 98% time spent in checking that the solutions are actually minimal we cannot get rid of. So right now we're at a point where all the parameters have been tuned well enough, except for this minimality check needed. So the rest, basically, no time is wasted in the rest of the solver anymore.
fine-tune the solver thing so hard, but the overhead is so high that it will.
Hello. Matthew, can you project your screen?
Hello, I can share. Okay, I will share my screen. Can you see the presentation? Well, screen. Is it okay? Do you see the presentation? Well, I don't know if I maybe.
Yes, that's good.
No, the present. Okay, okay, this is good.
So the next one by Matthew P. about application of SAT, and please proceed. We don't hear you. Can you hear us?
Oh yeah, so sometimes maybe you are not so close to the micro, I think. Can I start?
Yes, please start. Thank you.
Okay, so hello everyone, I'm Mathieu P from Clermont-Auvergne University, France. First of all, apologize for not being there in person. In fact, I came into India and after I get sick and I came back to France. So this will be a hello from France presentations. Indeed, as you said, it will be a work about the application of SAT to an optimization problem, which is the simple assembly line balancing problem with polar peak minimizations. So I will start just to present the problem by giving a short example. So we have a set of tasks and a set of workstations, and the first question is how to assign the task to the workstations. We also have a cycle time. In this example, the cycle time is 5. So we have to end every task before the end of the cycle time of 5. And in this case, we also have precedence constraints. So in this case, lexicographic precedence. These precedents are maybe little particular in this kind of problem because, in fact, for example, task 1 precedes task 2 means that either task 1 must be assigned to a lower workstation than task 2, or task 1 and 2 can be assigned to the same workstation, but task 1 must be done before task 2. So on the bottom of the screen, you can see solutions, a non-feasible solution. Why not non-feasible? Because of the precedence constraints. Because the instance said that task 1 must precede task 4, but when you look at the solutions, you observe that task 1 is on a lower workstation than task 3, so it is not a feasible solution. On the other hand, now on the bottom of the screen, you can see a feasible solution for the SILB 3PM problem, so which respect every constraints. And now we can compute the value of the solution, which is 12. In fact, the value of the solution is the power peak consumption of the solutions. So each task has a power consumptions, and at the beginning of the solutions, at time 0, it is executed at the same time task 1, 2, and 4. So the total power consumption at the beginning is 4 plus 4 plus 4 equal 12. Then, after 2 units of time, task number 2 ends and task number 3 starts. And then the total power consumption is now 10, 4 plus 2 plus 4. And finally, after 3 units of time, task number 4 ends, and now the total power consumption is 4 plus 2 plus 0 equals 6. So the worst situation was at the beginning when the total power consumption per unit of time was 12. So 12 is the value of this solution. Now, in fact, this was a feasible solution. I will just come back, but not an optimal one. To do a better one, we can just take task number 4 and delete it like this one. And now we have a better solution whose power peak is 10. Why 10? Because at the beginning of the solutions, we have a total power consumption or 4 plus 4 plus 0 equal 8. And then after 2 units of time, task number 2 ends, task number 3 and 4 start, and now the total power consumption is 4 plus 2 plus 4 equal 10. This is an optimal solution. Okay, so this is the SLBP3 problem, and in state of the art, there exists an integer linear program to solve this problem. So I will just introduce it a little bit. So this integer linear program for the state of the art uses 3 types of decision variables. So first, a Boolean decision variables x, and a given workstation x says that the task is or is not assigned to these given workstations. We also have in state of the art this Boolean decision variables s. So for each task and with each unit time, s says that that task start or does not start at this given time. And finally, we have an integer decision variables, which is just the value of the power peak consumption of the solution. Then, of course, there are many constraints to the problem. For example, each task must be assigned to exactly one workstation, which is the constraint in the middle of the screen. And finally, the objective function is trivial in this case because we want to minimize the power peak of the solutions. Just to put it on the screen, you can see now the complete integer linear program proposed in the state of the art. And I remember when I saw a presentation of this work and when I read the paper, I found that it could be a great problem to use SAT technology. Why? Because in fact, the problem, the model, the integer linear program is almost Boolean. Only one variable is integer, the other one are Boolean, and I thought maybe it's okay, we can just can use the SAT technology. And also, when I saw the instances on the problem, in fact, it appears that finding a feasible solutions is already difficult for this problem. Why? Because the number of workstations and the cycle time is as smaller as possible. So I found I was going to use that to try to solve this problem. And this is the contributions I will talk in these presentations. So basically, I'm just saying I will ignore for now the optimization part of the problem. I will talk it later, and I'm just wondering how to model this problem, how to find a feasible solutions into SAT. The decision variables, we use almost the same decision variables. So we have variable x, variable else, which are in the integer linear program. We also added one variable a to know if a task is or is not active at a given time. In fact, these variables is mainly useful for the optimization part of our approach, so you can ignore it now. Also, we basically model every constraint into SAT. So in the middle of the screen, you can see a representation, an encoding of the constraint saying that each task must be assigned to exactly one workstation. In fact, it's a naive encoding. It's a pairwise of encoding of the constraints. And of course, as I'm modeling the feasible part of my SLB3 problem, I do not have any objective functions. I will just find feasible solutions. So the complete initial SAT model is this one. It is really close, in fact, than the integer linear program. We can just see it as translations. Maybe we used new variable a to simplify, in fact, the constraints. Also, we added some pre-process technique and simplification constraints. To understand it, at the bottom of the screen, when it was a solution of first instance, and when you look at it, you can understand that in fact, task number 4 cannot be assigned on workstation 1 and 2 because of the precedence constraints. Because task number 4 is preceded by task number 1, 2, and 3, and the total processing time are sufficient to cover workstation 1 and 2. So we can, in a processing process, in a processing treatment, forbid task number 1 to be assigned to workstation 1 and 2. And this is, in fact, the first line of the additional constraint. The same, but just for some part of the time on one workstation. For example, task number 3 can be assigned on workstation 2, but it cannot be assigned at the beginning of the time. And finally, last simplification constraint is just saying that long task must be active at the middle of the time. For example, the trivial part is if you look at task number 1, in fact, it is active every time because the processing time of task number 1 is the same as the cycle time. So we added the simplification constraints, and we also used it to remove some redundant constraints and clauses from the initial constraint from the last slide. Okay, now I just, in fact, model the problem of finding a feasible solution, but I don't want a feasible solution. I want an optimal solution. So I will explain how to find an optimal solutions to this problem using SAT. And in fact, I will just describe a SAT-based algorithm. So I will input my SAT model into a loop, finding feasible solutions and adding constraints to remove some patterns of solutions to finally find the optimal one. So I take my instance on the top of the screen, and I model how to find a feasible solutions by the SAT model that I described before. Then I call a SAT oracle to get a feasible solutions. The SAT oracle will know anything about the value of the solution, but it's not important. I just call a SAT oracle and I get a feasible solution. So as the first time I call the SAT oracle, he says, okay, I have a feasible solution. This is the one of the screen. It doesn't know anything at all about the value of the solution. It's not important. We take the solution returned by the SAT oracle and we analyze it. We analyze it to find why this solution is not better than the best known solution. In this case, this is the first solution, so this is the best known solutions, and we analyze it, we compute that the power peak is 12, and it is 12 because we assigned, we executed task number 1, number 2, and number 4 at the same time. So the SAT oracle is just sleeping, in fact, and we add new constraint to the model to forbid task number 1, number 2, and number 4 to be executed at the same times. Notice that in this solution, we just exhibited one cause of the value of the solution. If we add several causes, we added several set of clauses to forbid them. Okay, so now we added new constraint to the SAT model to forbid a pattern of solutions, possibly an exponential pattern of solutions, and we call again the SAT oracle to get a new feasible solution. So at the second iteration, our SAT oracle says, okay, I have a new feasible solution. This is the one. We take that solutions, we analyze it to get the value of the power peak and the causes of why this solution is not better than the currently best known solutions. When we analyze these solutions, we say, okay, the power peak is 10, and it is the best known solutions, and it is not better because of task number 1, 3, and 4, which are executed at the same time. So the SAT oracle is still sleeping, and we add constraints to the model to forbid task number 1, 3, and 4 to be executed at the same time. Then we call again the SAT oracle, and at the third iterations, our SAT says that there is no feasible solution. The conclusion is that the unoptimal solution to the SILB3 problem is the best known solution among all of the iterations of the algorithm. In this situation, it was just the last met solution. Okay, so it is a SAT-based approach that I described. So we experimented it on state-of-the-art instances, and the results are quite promising. In fact, except on, for instance, trivial instances, the SAT-based approach showed better results for now than the existing integer linear program. Well, so maybe it's a good SAT-based approach problem, and that was the idea we had. And more generally, I think as people working on constraint programming, we must study a problem on which maybe people didn't have the idea to try constraint programming approach, satisfiability approach, but very many work on this problem. For instance, when I showed cardinality constraints somewhere, I just used pairwise encoding cardinality constraint. Maybe other cardinality constraint must be good. Also, maybe a maxat approach, because in fact, I didn't want to use maxat for the first time. I did want to use SAT, and we used a SAT-based approach. But maybe we can encode the objective function into maxat. We saw some maxat presentation before and try it. And we have currently an internship which is trying to apply maxat and to compare SAT approach and maxat approach. And finally, for the more future work, maybe try a constraint satisfaction problem approach, constraint programming, or try to solve the SRB3 problem in incomplete solving, because in fact, in the previous slide, in the experiments, we can say that the instances are not huge, quite small. So to solve bigger instances, maybe incomplete solving can be good. So thank you for listening. And if you have any question.
Thank you. No questions.
Thank you for the talk. I didn't really catch the intuition for why you would need this, like just in the problem definition, this precedence constraint that you want to map your tasks to like monotonically to the workstations you have. So is there any intuition for a possible application why you would want that exact constraint? Because in scheduling, you have like the dependencies between tasks that you need the output of one for the input of the other, but I don't catch that for this kind of precedence constraint. So is there an intuition behind it?
Okay, yeah. There are common precedence constraints in these types of problem. I will explain. In fact, imagine, for example, a car factory, and let's ask the question that where the car in our mathematical problem? Cars are not workstations. Cars are not tasks. In fact, cars are the object on which you apply the task on the workstations. And from the point of view of the object of the car, these precedence constraints are just basic precedence constraints. Because when you are a car, at the beginning of the day, in fact, you go to workstation number 1. I will take these solutions. So at the beginning of the day, when you are a car, you go on workstation 1, and you execute on the car task number 1. Then, at the end of the cycle time, in fact, the car will just go to the workstation number 2. And we will execute on this car task number 4 and task number 3. Again, after the cycle time, the car will be on the third workstations, and we will execute on this car task number 4. So in the real world problem, in fact, at each moment, we have 3 cars, 1 car per workstations. And if you consider the point of view of the task, the precedence constraints, as we described mathematically, is just basic precedence constraint, because when you are on a workstation 2, you are after you were on workstation 1. So when you define precedence constraints saying that one task must be on a lower workstation than another task, in fact, it is just about time. It's just the representation of the problem which is important to in fact model the time representations in the real world. Because in fact the cycle time, it is not the end of the factory. It is the time where each object goes from a workstation to an upper workstation.
Yeah, that
Is
makes
it
a lot
clear?
of sense. Thank you. Yeah.
Okay, one more question.
Hello, thanks for the talk. I wanted to ask if you analyzed how many calls to the SAT solver you have to make, because if I understood it correctly, you might need to go through all feasible solutions to like find the optimum, and then I guess this could be like a bottleneck because there might be like exponentially many feasible solutions, and so I assume that encoding the objective using some variables might significantly speed up the process.
Yeah, that's a good question because indeed the number of feasible solutions can be exponential. However, the idea why to do something like that, because in fact, when I say, for example, on the screen, when I say I don't want task number 1, 2, and 4 to be executed at the same time, I can remove an exponential number of solutions and in one iterations. So if it's not a problem for me to have an exponential number of solutions because I can remove an exponential number of solutions at each iterations. However, I agree that in fact, in theory, you can need an exponential number of iterations to end our set-based approach. And in such instance, maybe a maxat approach would be quite better than our set-based approach. In fact, in the experiments we did, there is one instance, I remember it is Buxe 1, when we didn't, our set-based approach didn't end because in fact, the number of workstations and cycle time was not as much smaller as possible. There were a little gap. So because of that, the number of pattern of feasible solutions were really huge. And even if we think we found the optimal solution after a little amount of time, in fact, for the rest of time, we are just enumerating a lot of pattern of exponential a lot of pattern of solutions. So there are some instances where indeed the number of iterations is too big and it is a problem to be efficient. Maybe in this regard, maxat can be better, or maybe just encoding also adding only the constraint saying that we do not want to have this task, but maybe adding also a constraint like in maxat algorithm saying that we want the optimum function to be small. But yeah, I think maxat can be good for some instances in which the number of pattern of feasible solutions is really too big.
Okay, thank you.
Yeah, just a follow up on the same question. What SAT solver do you use? Do you do incremental SAT solving?
Where we use the glucose as a solver for this experiment.
So the SAT solvers are incremental, right? They are just
Yeah,
like one call.
indeed incremental, because yeah. If you do it not incremental, indeed it will be a bad idea because we have to reconstruct. It is important in this situation to have incremental SAT solving. In the experiment, in fact, what happened usually is that the first time we call the SAT oracle can be quite long to find one feasible solution. But after, as our SAT solver is incremental, for the second iteration, for the second time we call the SAT oracle, in practice, the solving time for the SAT oracle is quite short, and after it grows slowly. So yeah. If you try something not incremental to SAT-based approach, is not good.
Yeah, I completely agree with you. So maybe you could also consider partial cardinality constraints. So Maybe if you want to encode the peak energy consumption, maybe instead of giving to the all tasks in the same time step, maybe partial of them, because you are finding the high peak task, right? Maybe give only some of
Yeah.
them and give cardinality constraints, so you can reduce the solver calls that way. Or
Again,
somewhere in the
please.
middle. Yeah.
Oh,
Instead of
okay.
just giving the all explicit clauses, maybe you do
Yeah.
some partial encoding of cardinality constraints for the peak consumption. So then you can reduce the calls while not doing max SAT directly.
Okay. Yeah.
Perhaps.
Yeah. Anyway, we are trying MaxSat currently with an internship, so we will see the difference between our approach and the MaxSat approach. I think MaxSat can be quite good on this problem.
Yeah. Thank you.
Thank you.
All right. Thank you very much. I think we are running over the workshop time. So thanks again for the speaker.
Thank you all.
And I think we can go for lunch now.
Yeah. Before we move for lunch, I have just very quick announcements to make. First of all, just to remind you all, we are inside TCS premises, so we have to follow the TCS security protocols and all the different protocols that are set here for everyone's convenience. First of them is photography is strictly prohibited inside TCS premises, so please refrain from doing any photography. We thank you for your support. Second thing is no food and beverage is allowed inside MPH area. So this is the MPH area as we like to call it. So we request your cooperation in that regard as well. Third thing, for those people who are coming for the first time today, the lunch will be served at a different place. So if you exit the MPH area, you have to take a left. There's a 1-minute walk. People will be there to guide you. It's known as Executive Dining Room, EDR. The lunch will be served there. And in case while registering, if you have placed any special food requests such as Jain food and all that, please get in touch with Pawan. Pawan is the captain of our food arrangements. I'm sure he might have followed them and prepared a different bento box for you. So thank you again and hope to see you again at 2 p.m.